Hi, welcome to me313 Mechanical Engineering Thermodynamics. The topic of this video is cascade refrigeration, and the section in the textbook is 11.8. Here are the three learning outcomes. At the end of this, you'll know the major components that make up a cascade refrigeration system. You'll understand why cascade refrigeration can have a higher COP compared to standard vapor compression refrigeration. And you'll be able to solve for the conditions and the COP in a cascade refrigeration system. So first, let's go ahead and just review standard vapor compression refrigeration. So you've seen this in the previous video, and I have it again over here on the left. So let's just kind of put our points. We have point 1 over here in the lower right. It's going through a compressor. I have it drawn as an isentropic compressor up to point 2. Then we have the heat exchanger. Heat is leaving. Usually this results in something pretty close to a saturated liquid. That saturated liquid is then run through the throttling valve. This is an isenthalpic state down to 4. Isenthalpic, remember says that the enthalpy is equal to a constant. Couple things to point out. Remind you again, the cooling capacity is the area underneath the curve right here. And the other thing is this temperature, call it T sub L, is really dictated by what the lower pressure is. So the lower pressure in my cycle really determines how cold my freezer is. So let's go ahead and now look at what's called cascade refrigeration. And if we look at, for example, just the top of the diagram here, what you see again is a compressor, a heat exchanger, a throttling valve, and then what we have is an evaporator. So it looks like just a typical vapor compression refrigeration system. But below it, we actually kind of looks like, again, just another standard vapor compression refrigeration cycle. And they're coupled with this heat exchanger, which where the heat from the lower system, lower on the diagram here, in its condenser, is actually losing heat up into the evaporator of the upper system. And what we'll see is that this system right over here actually has a higher coefficient of performance at the expense of having to add some additional components. As you see, we now have 2 compressors and a heat exchanger, where before when we had a single compressor, when we didn't have the heat exchanger in between them. Right, so let's go ahead and draw this diagram on a TS diagram. And so I'm going to start off on this bottom cycle that I have over here. And so we'll start off and put point 3 right there. Typically is a saturated liquid running through a throttling valve down to point 4. That would be a mixture. And then it's going to absorb heat in the freezer box, and we'll go through a compressor. And I'll go ahead and just draw this right now as a isentropic compressor, so it'll be straight up. And then this will be the higher pressure that it is operating at. So this is point 4, this is point 1, and this up here is equal to point 2. Okay. But now let's go ahead and look at the upper cycle, which is 5, 6, 7 to 8. And I'm going to go ahead and change my pen color. Go ahead and draw this one in blue. And so if we look here, again, we've got kind of the same type of cycle where I have point 7, that's usually a saturated liquid, running through a throttling valve to some point 8 down here. And these are separate cycles. They're not coupled. They're coupled with heat, but they're actually, the pipes are separate. So these are completely different fluids, if they want to be. Over here, 2.5, and then again, I'll draw an isentropic compressor up to 2.6, and at that higher pressure right there. Okay, so here are the 2 cycles, and because these are separate systems, they can be operating at completely separate pressures. But let's go ahead and first of all look at why this might have an increased cooling capacity, or an increased coefficient of performance. Remember, this area right down here is equal to the cooling capacity. And so this is now the cooling capacity of my cascade refrigeration system. Now, if I wanted to go ahead and run a freezer at that same temperature with a single system, just to have this upper system and run with a larger compressor, it would have gone down, for example, that dashed line there. So it would just be a single system. And we realize, so there's this additional cooling capacity. I'll go ahead and hash it this way on the left-hand side. We also have a smaller work requirement, because again, if we were to operate this on a single cycle, a single compressor, we would have had to have gone all the way from point 1 up to a point 6 up here. I'll call it 6 prime, and there would have been some additional work. And since the coefficient of performance for a refrigerator is equal to QL over W, increasing QL and reducing W clearly increases the coefficient of performance. Now, a couple other things I want to mention here. is that I have drawn these lines 5 and 8, and then this line right over here, 3 across, at different temperatures, and they're up, so they would be at 2 different pressures as well. And remember, the heat has to go from the lower cycle to the higher cycle, so it needs to go in that direction. So this red line would need to be above the blue line, and the farther apart they are, the better heat transfer you're going to have. You'll see the diagrams in the book. Often we'll draw them at the same temperature and the same pressure, which is theoretically possible, but from a functional point of view, it would be really difficult to get very much heat transfer going on. So you kind of want a large distance in between that so you can have efficient heat exchanger. But notice that if as we were to do that, so say for example I was to move this up a little bit, so I'll call this point up here 3 prime, so that I could go ahead and have a larger temperature difference between that and the blue line. Well, that's going to come at a consequence of then I would be operating here, and again I'm going to start losing some cooling capacity. So you see there's a trade-off going on. I'm going to have a better heat exchange performance in my heat exchanger with a larger delta T there. But what I'm going to do is the benefits I'm getting from an increased cooling capacity are going to be decreased. And clearly as I move up to 0.7, then I'm going to the single stage compressor. All right, let's go ahead and solve the cascade refrigeration system, and I'm going to do the example that's in the book, and so I'll go ahead and do this in EES instead of by hand as it's done in the book. So here we go ahead, and I have this in EES, and so let's go ahead and just look at some of the specifications and some of the things that might be different from what you normally see. First of all, we're going to do this problem with a refrigerant R134A. And so I'm not to type the word R134A every time. I'm going to define a string variable with that name. And so what's different, this is just like any other variable in EES, except since it's containing a string or a listing of characters, I need to go ahead and put this $sign after the name. And this just tells EES this is not a numeric value, this is actually a string value. And this is a little different than some other programming languages. But you could think of it as sort of a variable type declaration like you might see in C++. So that's only different, and I'm calling the variable R1. And then I've got my mass flow rate at 0.02. And now I'm defining the points that we know when we've got saturated liquids and saturated vapors, and that's what points 1, 5, 3, and 7 are. And you can go back to that TS diagram and review that those are correct. I'm operating at a high pressure of 800, a low pressure of 140, and a middle pressure of 320. Now, we're going to go ahead and have both the upper cycle and the lower cycle have that same middle pressure, which means that there's not going to be any temperature difference. This is going to be the closest they could be to go ahead and follow what's in the book. But recognize normally we would want 2 middle pressures to have an efficient heat exchanger. Then we've got our isobaric steps, and I label which ones are at the low pressure, that middle pressure, and at the high pressure. And we'll go ahead and keep it simple and straightforward at this point. We'll have an isentropic compressors from 0.1 to 2 and 0.5 to 6. And then we have the isenthalpic valves, which is going from between 3 and 4 and points 8 and 7. So if I go ahead and solve that, at this point, if I go ahead and look at my array table, I realize I have every pressure specified 1 through 8. And then at 4 of the points, I know the entropy, and at the other 4 points, I know the enthalpy. So therefore, I have 2 independent intensive variables. So I can now go ahead and start solving for things like what my coefficient of performance are. But one of the things that I need to know, and let me just go ahead and back to my diagram to remind you. I'll go back to my presentation here. Remember, this bottom cycle is completely separate from the top cycle. And so there's going to be a mass flow rate going through the upper cycle, a mass flow rate going through the bottom cycle, and those are clearly don't need to be the same. And in fact, they don't even have to be the same fluid, let alone at the same mass flow rate. So the problem specified the mass flow rate in one loop, but we need to go ahead and define it in the other loop. So what I defined up at the top is M2 at 0.05. We need to determine what it is at 0.1, so you know how much material that we are pumping, and we actually are compressing, and we actually get that from a energy balance over the heat exchanger. So let's go ahead and look at that energy balance over the heat exchanger here. So here I've got the mass flow rate of 2 and the difference of 5 and 8 and the mass flow rate of 1. So now this is going to go ahead and solve for M1 and tell me what the mass flow rate is on the lower loop. The upper loop is 0.5 to 8. And once I have done that, I can then go ahead and define a few enthalpy values and then find my coefficient of performance. All right, so there's 2 compressors in this. We've got one in the lower loop, and that's mass flow rate 1, one in the upper loop, and that's mass flow rate 2. So there's my total work input. And then my QL, which is the desired product, is only in the lower loop, so that's why I need to know what the mass flow rate is of 1, and then the difference of H1 and H4. In other problems, we didn't actually need to know the mass flow rates. We could do all of it with like a little W and a little QL, but we can't do that in here, so we need to know our relative mass flow rates. So we go ahead and look at our solution. We see our coefficient of performance is 4.474. Go back to the earlier example that we did a couple videos back, or look in the textbook as well. You'll realize this is a larger coefficient of performance than if we operated between just the upper and lower pressure limits with a conventional vapor compression refrigeration cycle. And let's go ahead and look at just what the temperature is of this is. And so one last thing I'm going to do is, since I know what, for example, the pressure and the enthalpy is at every point, I can go ahead and just find what the temperature is. And in addition to knowing your coefficient of performance, it's often nice to know what the temperature is that you're operating at. And so if we look here, we're over here at 0.1 at minus 18.77 and 0.4. That's the lowest temperature in the cycle. So that says my freezer is operating at about minus 19. And if I look at my highest temperature, which is up here, I have 34 going down to 31. So that's clearly above room temperature. So I would expect that this refrigerator would be able to operate inside a standard room temperature. Those are important numbers to look at because, for example, maybe my freezer box isn't cold enough or too cold. You clearly have one that's too cold. And then if the temperatures that are in the heat exchanger, the coils in the back are not warm enough, you wouldn't be able to lose that temperature into a range. So you need to make sure you look at those temperatures to double check that your answers seem to make some sanity, or seem to make our sense have some sanity to them.